Welcome to this last video of my playlist about carbon dioxide. This video is about the decarboxylation of carboxylic acids. In most examples, the carboxyl group was replaced by hydrogen, but I've also included oxidative and CC bond forming decarboxylations. The main reason why decarboxylations are common, more common than for instance the cleavage of ketones or aldehydes, is that carbon dioxide is so stable. I've discussed this stability at length in the second video of this playlist. Decarboxylations can proceed by a number of different mechanisms. When a carboxylic acid carries an electron withdrawing group at the alpha carbon, CO2 can be readily cleaved off from the carboxylate to yield a stabilized carbanion. The stronger the electron withdrawing effect, the easier the decarboxylation will become. The carbanion can react with any electrophile present in the reaction mixture, for instance protons, halogens, or various carbon electrophiles. I'll show you specific examples in a minute. Another mechanism is beta elimination of a leaving group, as sketched here. This can also occur if the leaving group is attached to a heteroatom, not to carbon. An example would be alpha amino acids with a leaving group at nitrogen. Another important mechanism is the decarboxylation of carboxyl radicals. These are formed by chemical or electrochemical oxidation of carboxylic acids or by heating acyl peroxides. Most carboxyl radicals decarboxylate quickly and irreversibly, again because of the high stability of CO2, and this reaction is a good method to generate alkyl or aryl radicals. These radicals can dimerize, as in the Kolbe reaction, but that requires a high local concentration of radicals. This can be achieved on the surface of an electrode, and radical dimerizations occur therefore usually upon electrochemical oxidation of acids. If the radicals are generated in the presence of halogens, halogenation at carbon can occur, as for instance in the Hunsdiker reaction. Radicals can also add to olefins or arenes. With an excess of oxidant, radicals can also be oxidized to carbocations, which then react with any nucleophile present in the reaction mixture, including water or alcohols. Another decarboxylation mechanism is the decarbonylation of acylium cations. Such reactions proceed readily if the intermediate carbocation is well stabilized, as for instance in alpha-alkoxy acids or aryl acetic acids. Here are some acids at the borderline of thermal stability. Those of the upper group are more or less stable at room temperature, but can decarboxylate when heated. The lower group, including nitroacetic or acetoacetic acid, tend to decarboxylate already at room temperature. Small amounts of impurities or solvent residues can further decrease or increase the stability of these acids. I'll show you now some specific examples of decarboxylations, beginning with simple aliphatic acids, followed by benzoic and heteroaromatic acids, acrylic and propiolic acids. Esters can sometimes also be decarboxylated directly, without saponification, and at the end I'll show you some examples of ester decarboxylations. Simple fatty acids are thermally quite stable. The pyrolysis of acetic acid at 700 degrees Celsius, for instance, does not yield carbon dioxide and methane, but ketene and water. Certain transition metals can, however, promote the thermal decarboxylation of aliphatic acids. Here, palmitic acid yielded a mixture of mostly alkanes and olefins when heated with a small amount of ruthenium carbonyl. A cleaner decarboxylation to a terminal alkene can be achieved by activation with a sacrificial anhydride. In this example, pivalic anhydride and catalytic palladium brought about such an olefin-yielding decarboxylation. Instead of pivalic anhydride, an excess of acetic anhydride can also be used. In this optimized example, the yield of terminal alkene was again about 60% only. Acetic anhydride had to be dosed carefully, and a catalytic amount of bisphenol was also required. Acetoacetic acids are much easier to decarboxylate than fatty acids. Mere refluxing in carbon tetrachloride for 1 hour was enough for a complete decarboxylation of the intermediate keto acid of this example. This acid was formed by Claisen rearrangement of an allyl acetoacetate. In this interesting example, the dianion of chloroacetic acid was first condensed with protected tyrosine methyl ester to an intermediate chloroacetoacetic acid. After acidification with acetic acid, the decarboxylation was complete after 12 hours at -45°C. The large excess of dianion was necessary because one equivalent was protonated by the Boc-protected amino group. Some acids can decarboxylate both under acidic or alkaline conditions. Here, the potassium salt of a nitrophenyl acetic acid decarboxylated completely by stirring in DMF at 50°C for half an hour. Here, a benzothiazolyl acetic acid was decarboxylated by heating with hydrochloric acid and ethanol to 60°C for 3 hours. Thus, also electron-rich aryl acetic acids may lose carbon dioxide upon warming. This is an example of the decarbonylation of a pyralic acid-derived acylium cation. During an attempted Friedel-Crafts acylation with pyraloyl chloride, mainly terz-butylated products resulted instead of the expected phenyl ketone. Here, an aqueous solution of proline was heated to 235°C under hydrogen with a palladium catalyst. The main product was pyrrolidine, which was formed along with some byproducts, mostly pyrroline and 2-pyrrolidone. This reaction probably also proceeded by intermediate formation and decarbonylation of an acylium cation, followed by hydrogenation. This is an example of the oxidative decarboxylation of an alpha-methylthiocarboxylic acid. Treatment with N-chlorosuccinimide and sodium bicarbonate at room temperature for 2 hours yielded a ketone. The mechanism was probably better elimination of hydrogen chloride and CO2 from an intermediate chlorosulfonium salt, followed by hydrolysis. One famous decarboxylation strategy is the Barton decarboxylation. Photolysis of esters of 2-pyrithione causes homolytic cleavage of the nitrogen-oxygen bond and the formation of a carboxyl radical and a relatively unreactive 2-mercaptopyridyl radical. After a fast decarboxylation of the carboxyl radical, the alkyl radical will be reduced to an alkane if a hydrogen atom donor is present. In this example, the hydrogen donor was chloroform. 2-pyrithione is an inexpensive biocide produced on a large scale and thus readily available. Photochemical transformations, however, are usually impossible to scale up and can even be difficult to perform on a laboratory scale. Most chemical reactions turn dark because small amounts of intensely colored dyes are formed as byproducts, and this is also the case for photochemical transformations. Such impurities prevent the light from reaching deeper into the reaction mixture, and thereby strongly slow down the reaction. Moreover, starting materials must be exceedingly pure and dye-free for photochemistry to work. That is the reason why I do not usually choose photochemical transformations as examples. I've done a lot of photochemistry myself, but would rather avoid it if possible. Carboxyl radicals can also be generated by heating diacyl peroxides, as in this example. An ethyl radical was generated by heating propionyl peroxide to 100°C. This radical added to an N-phenyl metacrylamide, which then cyclized to an indolinone. Re-aromatization probably occurred by hydrogen abstraction by the peroxide, as sketched here. With benzoic acid-derived peroxides, this reaction did not work. Heating acyl peroxides with styrenes and alcohols can yield benzylic ethers. Because alcohols do not react with carbon-centered radicals to yield ethers, an oxidation step was required in this case. I've sketched here one potential mechanism. The pentyl radical resulting from homolytic fragmentation of the peroxide added to the styrene to yield a benzylic radical. This radical was then oxidized by iron 3 to a benzylic carbocation, which then reacted with methanol. Iron 2 then reduced the peroxide by single electron transfer to a new carboxyl radical, while being itself re-oxidized to iron 3. Thus, a catalytic amount of iron was enough to drive the reaction to completion. This is an example of oxidative decarboxylation of an aryl acetic acid. Again, neither acids nor bases were required, only oxygen and catalytic copper acetate in DMSO. Another type of oxidative decarboxylation is the Hunziker reaction. In the classical procedure, bromine is added to a silver carboxylate, but a number of more convenient modifications have been reported. In this example, the oxidant was diacetoxyiodobenzene, and the brominating decarboxylation already proceeded in dichloromethane at room temperature. The ketone was not brominated. With N-iodosuccinimide and iodine, alkyl iodides could be prepared directly from carboxylic acids. A number of procedures have been developed to convert carboxylic acids into amines with loss of one carbon atom. These include some famous name reactions, for instance the Lawson, Schmidt and Curtius rearrangements. In the Lawson reaction, an acid is first converted into a hydroxamic acid by acylation of hydroxylamine at nitrogen. The hydroxamic acid is then dehydrated to a nitrene, which rearranges to an isocyanate. In this example, instead of preparing and isolating a hydroxamic acid, the starting acid was treated with a dioxazolone as an activated form of hydroxylamine. In the presence of DBU, a clean decarboxylation to an acetamide occurred. This would be one potential mechanism, proceeding through an activated hydroxamate, a nitrene and an isocyanate, just like the classical Lawson rearrangement. Let's check some aromatic decarboxylations. Aqueous solutions of phthalic acid could be heated to 250 degrees Celsius for 1 hour without any noticeable decomposition, but above 300 degrees Celsius a clean decarboxylation to benzoic acid occurred. Benzoic acid first started to decarboxylate when heated to above 400 degrees Celsius. With catalytic copper oxide and NMP, phthalic acid monoesters could be cleanly decarboxylated already at 140 degrees Celsius. Heating an aqueous solution of naphthoic acid with palladium on charcoal to 250 degrees Celsius gave mostly naphthalene. These conditions could not be used, however, to decarboxylate fatty acids. Polyhalobenzenes are quite acidic and can sometimes be deprotonated with alkoxides. The thermal decarboxylation of halogenated benzoic acids is therefore easier than that of donor or unsubstituted benzoic acids. In this example, tetrafluoroterephthalic acid was decarboxylated twice, just by heating in DMF to 100 degrees Celsius. Also 2 or 4 hydroxybenzoic acids decarboxylate more readily than expected. These compounds are phenylogous carbonic acids or vinylogous ketocarboxylic acids if we draw the ketone tautomer of the phenol. In this example, heating a 4-hydroxybenzoic acid with dimethylanilene to 200 degrees Celsius for 2 hours gave 80% of the decarboxylated phenol. Benzoic acids with 2 or 3 electron-donating substituents in positions 2, 4 and 6 can be decarboxylated with catalytic palladium-2 in a mixture of DMSO and DMF. Although the yields were high in some instances, the scope of this reaction was rather limited. Hunziker-type halogenating decarboxylations can also succeed with aromatic acids. Here, a substituted nicotinic acid was converted into 3-bromopyridine by heating with tetrabutylammonium tribromide in acetonitrile. Transition metal catalyzed decarboxylations sometimes yield organometallic intermediates suitable for C-C bond-forming reactions. In this example, a substituted biphenyl was prepared in high yield from a benzoic acid and a bromoarene. This example is similar to the previous one with still lower amounts of copper and palladium and without any phosphine ligand. Here the new C-C bond was formed between a benzothiazole carboxylic acid and the unsubstituted 4 position of a methyl benzoate. Unfortunately, a large excess of silver carbonate was required as oxidant. The scope was limited to the combination of electron-rich with electron-deficient arenes. One convenient laboratory strategy for preparing styrenes is the decarboxylation of cinnamic acids. Depending on the substituents, such decarboxylations can proceed under surprisingly mild conditions. 2 or 4 hydroxyphenyl acrylic acids are particularly sensitive. Here a nitrocinamic acid was heated with metallic copper in quinoline to almost 200 degrees Celsius and the yield of styrene was only moderate. Knoevenagel condensation products of cyanoacetic acid can also decarboxylate upon heating, as in this example. Electrophilic halogenation or nitration of cinnamic acids can also cause decarboxylation. Here a nitrostyrene was obtained when 4-methoxycinnamic acid was heated with an excess of nitric acid in acetonitrile. This example is similar to the previous nitration. Electrophilic chlorination with bleach gave a chlorostyrene in moderate yield. Despite the low yield, this is in fact a convenient strategy for preparing the target compound. The starting cinnamic acid is readily obtained from chlorobenzaldehyde and malonic acid, and most other routes to selectively chlorinated styrenes can yield isomers and will probably be more expensive and tedious. CC bond forming decarboxylations can also succeed with cinnamic acids. In this example, heating the starting acid with an excess of ditersbutyl peroxide and catalytic iron in cyclohexane gave an excellent yield of a cyclohexylstyrene. This product was probably formed by addition of a cyclohexyl radical to the cinnamic acid, followed by decarboxylation, as sketched here. Even palladium-catalyzed vinylations have been reported. Again, the high stability of carbon dioxide led to a complete decarboxylation of some intermediate. Like hydroxybenzoic acids, hydroxycinnamic acids decarboxylate with ease. Terminal alkynes are acidic, and propiolic acids therefore particularly prone to decarboxylation. In this example, such a decarboxylation was brought about by heating an acetonitrile with catalytic copper chloride to 60 degrees Celsius for 1 hour. For many of the acids discussed by now, there are one-pot procedures where an ester of these acids is saponified and decarboxylated in one step. Some esters, where the corresponding acids would not decarboxylate readily, however, can be decarboxylated directly, without saponification. Beta-lactones, for instance, can cleave off CO2 under mild conditions, as in this example, to yield olefins. Similarly, the lactone obtained by Diels-Alder cycloaddition of benzene to the starting pyrone of this example underwent a clean cycloreversion to carbon dioxide and a substituted naphthalene. Despite the many reactions and the high energy and low selectivity of arines, the yield of the target product was 93%. Heating carboxylic acids does not always lead to a clean decarboxylation. One potential side reaction is the formation of ketones by Claisen-type condensation followed by decarboxylation of the intermediate keto acid. Here such a reaction was mediated by magnesium oxide and heating with a Bunsen burner. With iron powder, however, ketones can be obtained from acids already at a much lower temperature. Another potential side reaction is the formation of ketenes by elimination of water. The parent ketene is manufactured on a large scale by pyrolysis of acetic acid and is used immediately for the preparation of diketene, acetic anhydride, or other products. The pyrolysis of acetic acid proceeds with high selectivity, and decarboxylation to methane and carbon dioxide is only a minor pathway. In some of the examples above, carboxylic acids were activated by conversion to anhydrides. These will yield ketenes easily, as for instance here. Although decarboxylation could have occurred by beta elimination, this was not observed in this instance. Here are some more references which you can also find in the description of this video. As usual, you can find a PDF copy of the slides under the Community tab of my channel. This was the last video of this playlist. It wasn't all about synthesis, but I hope you found it interesting anyway. I at least had a great time making these videos and look forward to the next.